Welcome back. The objective of this video is to explore slant asymptotes in rational functions. In order to do that, though, we will have to do a review of polynomial long division, and you'll also see a review of synthetic division. So a slant asymptote occurs when the degree of the numerator is 1 degree higher than the degree of the denominator. The slant asymptote is the quotient polynomial found, so quotient implies division, found by using long division. Let's recall the long division algorithm, both numerically and algebraically. First, though, a slant asymptote, we've got 1 degree higher in the numerator and the denominator. So over here on the left, you might see that as like x raised to the n plus 1 over x to the n. A lot of times, for our purposes, we'll have like x cubed over x squared. So the numerator wins by just 1. So that's going to create a slant asymptote. The division algorithm really just says that our quotient, that means our answer from division, times our divisor plus any remainder equals the dividend, or what we're dividing by. So real simply, we know that 12 divided by 4 is equal to 3. So that means we also know that 3 times 4, or our quotient, this guy 3, times our divisor, the 4, what we're dividing by, is equal to our dividend, what's being divided. So real quick review of your 5th grade numeric long division, or as one of my higher level math teachers like to call it, he liked to call it goes into math, because something goes into something else. Very funny. So we're going to do 482 divided by 14. So our dividend is 482. Our divisor is 14, and our quotient will be the answer that we get. So in goes into math, we ask ourselves, well, how many times does 14 go into 48? So we ask ourselves, what's 48 divided by 14? Well, evenly, it goes in 3 times. So part of my quotient, my first digit here is going to be a 3, and then I multiply back. So 3 times 14. Okay, so 3 times 14 is 42. And then we subtract that whole quantity. And I get a remainder, if you will, of 6. 48 minus 42 is 6. And then I bring down the 2, and I start all over again. What's 62 divided by 14? And 14 goes in evenly 4 times. So we have 4, and then we take that 4 and we multiply back. 34 times 14 is 56. Then we subtract that whole quantity, and we get a remainder of 6. So our answer, if you will, is 34 plus 6 over 14, or 3/7. So our quotient here is 34, and our remainder is 6. And our answer, 34 and 6/14, or reduce our fractions, and 34 and 3/7. So our process stays the same with polynomial long division. We're going to do the exact same thing, but now we're just going to use the 2x as kind of our divisor. That's going to drive our division. So what I usually do is what I did over here with numeric long division, I ask myself that question, what's 6x squared divided by 2x? And that simplifies to 3x. So then I have 3x. And just like I did in the previous sample, I multiply back. What's 3x times 2x? Well, it's 6x squared. But then I have to do what's 3x times 1, which is 3x. And then we have to subtract this whole quantity. So that quantity is important. So I subtract that whole quantity. Our pluses become minuses. So we change all of our signs and we add. The x squareds drop out. And then we have 4x minus 3x. And I copied this wrong. I did not copy it wrong. I see what she did here. She switched these guys. So we're going to make that 5x plus 4. So 5x minus 3x leaves us with 2x. That's going to make our numbers nice and easy. And then we have a 4 to carry down. And then we're going to start the process all over again. We're going to say, what's 2x divided by 2x? Well, that's equal to 1, so that becomes part of our quotient. So 1 times 2x is 2x. 1 times 1 is 1. And then we subtract all that again. So we have a minus and a minus, an add, and we get a remainder of 3. So we could do a remainder of 3, but what we'll do is, like we did before, we're going to add this. So our quotient is 3x plus 1. Our remainder is 3. So our answer is 3x plus 1 plus 3 divided by 2x plus 1. Example 5, determine the slant asymptote of the function. We see here we've got x squared over x. And I'm not going to do long division on this one right away. I'm going to do synthetic division because we're dividing by a binomial that's first degree with a coefficient of 1. So we actually can do synthetic division on this guy. So I'm going to write down my coefficient. Well, my divisor is going to be -5. And my coefficients are 1, -6, and 7. I have all decreasing order of x, so I don't need any placeholders. And I'm ready to do my synthetic division. So I'm going to prime my pump. -5 times 1 is -5, and I get -11. And at this point, I really don't care, because now I've found the equation of my slant asymptote. It's just the equation of a line. I don't care about the remainder in my synthetic division. So the equation of my slant asymptote is y equals 1x minus 11. If you want a review of long division, how to do that, we can do that real quick. We're going to take x squared minus 6x plus 7. We're going to divide by x plus 5. So we ask ourselves, what's x squared divided by x? And that's simply x. And then we multiply back. X times x is x squared. X times 5 is 5x. We're going to subtract that entire quantity. The parentheses are important. It tells we're subtracting that whole thing. We get -6x minus 5x, and we get -11x plus 7. And then we start again. What's -11x divided by x? It is equal to -11. And at this point, we don't really care about the remainder. It's not part of our equation of our line, so that doesn't matter. But -11 times x is -11x. -11 times 5 is -55. We're going to subtract that entire quantity, and we don't really care about the remainder. This is our quotient is our answer of y equals x minus 11, and that's the equation of our slant asymptote. In sample 6, it says find equations for any asymptotes for the graph. So this could be vertical or slant. So we take a look at this, and we have x cubed over x squared. That's our highest degree, so we lead by 1, so we think there's going to be a slant asymptote here. So I'm going to go ahead and factor. And I factored the numerator, I factored the denominator. When I factored the x out, it was still factorable. And I see here that I have x plus 5 in the numerator and x plus 5 in the denominator. So we're going to have a whole here at x equals -5. So that's not an asymptote. That's just going to be a whole. Okay, but that's going to be important. So I've got a hole there at x equals -5, and the y coordinate of that hole, if I cancel those, do a little quick math in my head, that hole is going to take place at -5, and if I remember correctly, it would be -35 halves. So that's where our hole is. We have x minus 3 in the denominator, so we have a vertical asymptote at x equals 3. So we got one of our asymptotes. But now we still need the slant asymptote. Well, the x plus 5's cancel, And our equivalent function here, if I multiply back, h of x, x squared minus 2x in the numerator, and x minus 3 in the denominator. I think everything correct here. I saw I made a mistake in my factoring. So my factors of the denominator, x plus 5 times x plus 3. Now it's going to be easier to go ahead and do synthetic division to find our slant asymptote. Our divisor is -3. Our coefficients are 1 and -2 and 0. Prime my pump. -1, -3 times 1 is -3. I get -5. So my equation is x minus y equals x minus 5. And that's the equation of our slant asymptote. It's the equation of a line, so we don't care about the remainder. And if I did long division, I would get the exact same thing. In example 7, we're to determine if any of the following rational functions have a horizontal asymptote, a slant asymptote, or neither. So let's take a look at these. In example A, our leading coefficients, 3x over x squared. So we're going to evaluate the limit as x approaches positive or negative infinity. And this function is going to 0 because the denominator is getting much bigger. So our horizontal asymptote is at y equals 0. In sample B, we have 5x squared plus 3x minus 2 over 2x squared minus 3. So we're going to battle between the 5x squareds and the 2x squared. And that's going to look like that. We're going to take the limit, and that's going to approach 5 halves. So our horizontal asymptote is at y equals 5 halves. Example D is going to look a lot like example A as x gets really, really big, or as we test the limit as x approaches positive infinity. That denominator is going to get huge. That numerator is going to stay at 6. That whole fraction is getting closer and closer to 0. So we could write it as x to the 0 versus x squared, and we'll have a horizontal asymptote at y equals 0. Finally, in C, we have a slant asymptote in this guy because we lead by 1. We're going to have to do a little bit of long division here. We're going to divide by 2x plus 1. This isn't synthetic division eligible. We'll put things in decreasing order of x. We have a placeholder for 0x. Got to remember that. And then minus 8. So we go ahead and divide. What's 3x squared divided by 2x? And that simplifies to 3 halves. I swear to God, Jean Adams is killing me here. So she changed it to 4x squared because the numbers work better, because she figured out what I just discovered. So we're going to start all over. So we're going to have what's 4x squared divided by 2x? Well, that's 2x, and we're going to multiply back. And we get 4x squared plus 2x, and then we're going to subtract that whole quantity. So when we subtract all that, we get a negative 2x minus 8. We ask ourselves, what's 2x divided by negative 2x? It's 1, and that's all we need. So our equation of our slant asymptote is that y equals 2x minus 1. And that's our introduction to slant asymptotes in graphing rational functions. And you'll get some more practice with this when I see you in class.